Hello, I'm Nick. I'm going to be talking to you guys today about the wonderful world of paired t-procedures, or paired data. This is a special type of hypothesis testing, which we found in the Practice of Statistics, 4th edition, section 9.3. Before we delve into paired t-procedures, I'm just going to quickly run over hypothesis testing, just so that this video does not get too confusing too fast. So, just starting out, a hypothesis test is a test where we get a set of data and we take hypotheses and we test them, basically, to see which one is correct and which one isn't. So, the two hypotheses we have are the null hypothesis, H null, and the alternate hypothesis, H A. So these hypotheses are different, only the fact that H null is what we already know and H is what we want to prove. So to determine which is which, you will have either H null or HA. First, to start out, for the null hypothesis, you want to determine what you already know. So there's three different variables that you could use. You could either use P for probability, or mu, or X bar for counts or means. Then, for null hypothesis, you will have an equal sign, because that's what you know. And then you all have to give it a constant, because that's what the number that you know. Let's say the probability was 0.34. Or in the count was like 17, the mean was like 18.25. The alternate hypothesis that will correlate with each of these will have to keep the same variable. So let's say H sub A, P, mu, and X bar. However, you will not have equal signs. You can have one of the following. You can either have does not equal to, you can either have less than, or greater than, or equal to, for either of them. Then you will keep having the constant, the number that you put down at the end. Alright, so then, when you have your two hypotheses, you need to define your variables. So you would have to say P is the probability of whatever context you have. So you would use this to determine, make sure you know what you're actually defining. Then you also have to define your significance level, which is determined by alpha. This is going to determine whether you choose the null hypothesis or the alternate hypothesis. If not given to you, you will take this as 0.05. So you have this. So the next step you do is you have to use your checks, as you always do. So your checks. There are three things you need to check. Check if the distribution is normal, the distribution is independent, or the distribution is random. All three of these must work, or else this problem won't go through. To test normal, there are a few ways to do it. For one, if you're given probability, you would have NP has to be greater than 10, and N1 minus P has to be greater than 10. P is probability, N is population. However, if you're not given population, you have to just rely on sample size. Sample size has to be greater than 30. If it's greater than 30, it's normal. However, if it's less than 30, certain checks have to become in play. For example, you need to test if your normal distribution line on your calculator if it's linear. If it's roughly linear, then you can assume that the distribution is normal. If anything that's less than 30. So that's your normal checks. Your independent checks would be the 10% rule. This is the 10% rule that 1/10 of the total population has to be greater than the sample population you're given. If this works with whatever sample you're given, it's independent. For random, usually the problem's going to tell you if it's random or not, either using SRS or just as random sampling. However, if it's not given, you must assume it's random, so the problem can go through. After these checks are done, you must then go find your test statistics, either Z or T. These two test statistics are very similar. For Z, you mainly use this when you have probabilities and you know the standard deviation of your population. The equation for finding your test statistic is Z equals P hat, which is probability of the population, minus P null, which is the probability that's given to you in your null hypothesis, over the square root of P null, 1 minus P null, over N, which is the population. This entire thing down here is the standard deviation. T you could use if you don't have population or the standard deviation of your population, but you have the standard deviation of your sample. To use T, you would have, it's very similar, it's X minus mu naught, which you would find in your hypothesis, over the standard deviation of your sample over root N, which is your sample size. This is your standard deviation. When you plug in your numbers, you'll get a number for these two test statistics. Then you'll go to the back of the book in either table A or B, A for Z statistic, B for T statistic, and find what your p-value is, your probability value. This would be a number between 0 and 1. It would be a decimal between there, depending on which one, or your test statistic. This is when you want to incorporate alpha again. So, if you find your p-value, and if your p-value is greater than alpha, you must fail to reject your null hypothesis. This means that you're not rejecting what you already stated. So you're basically reaffirming that there's not enough evidence to disprove H null. However, if P is less than alpha, then we must reject H null and assume HA. So that means there's enough evidence to show that H null is incorrect, so we must assume that HA is correct. However, this always has to be followed up with a detailed explanation of why we must fail to reject, with detail including what P is, what alpha is, and a good explanation of your context and what this means. So starting out with paired T procedures, you would of course use the T statistic, T equals X minus mu over standard deviation of sample over root N. However, this is a special type of procedure. This is when you're given two sets of data, which is different from the previous when you're only given one set of data. This is going to be something like using weight loss, or a change in height, or a change in time, or any sort of change problem, how something has affected something else and changed it. You're going to be given a before and after, and you have to compare those. It's really easy to do. Let's say you have a list of numbers. Let's say here's your table before, after. It's like 3, 2, 1, 0. This is before, and after it was 8, 4, 6, and 2, you would subtract one side from the other to get a new table for difference. So say 8 minus 3, that would be 5. And then 4 minus 2, that's 2. 6 minus 1, that's 5. 2 minus 0 is 2. So now you're given with a new table only one sample. You don't have to deal with both, you're just dealing with the difference. And now you can just continue your normal hypothesis testing as you've known easily after this. So let's run through a few examples and let's try to work it out step by step. Here's a good example of a paired T procedure problem that you might see. It reads, the question is about fluorescence in learning. We hear that listening to Mozart improves students' performance on tests. Perhaps pleasant odors have a similar effect. To test this idea, 21 subjects worked a paper and pencil maze while wearing a mask. The mask was either unscented or carried a floral scent. The response variable is their average time on 3 trials. Each subject worked the maze with both masks in random order. The randomization is important because subjects tend to improve their times as they work a maze repeatedly. The accompanying tables gives the subjects' average times with both masks. Do these data provide convincing evidence that the floral scent improved performance? Carry out an appropriate test to support your answer. So you can tell this is a paired T procedure because you're given 2 different sets of data, the unscented seconds and scented seconds to finish the procedure. So what you would do in this kind of situation is immediately just break this out into one separate sample. So what you would do is make a new table for difference, right? Like diff seconds. And go through individually on what's the difference for each individual person. So if you go through your calculator, let's say I want to do unscented over minus scented. Just gonna make sure you note that somewhere. Unscented minus scented. So you take 30.60 minus 37.97. That gives negative 7.37. And do that down the entire row. So then 48.43 minus 51.57 minus 31.14. Or 3.14, my apologies. See, I'm going to quickly run through this and come back as soon as I'm finished doing this thing, the calculations. Be right back. I'm back, and I've found my new set of data. I've subtracted the unscented minus the scented, and now I have a whole new set of data that's going to have one sample, make it much easier, go back to normal hypothesis testing. So, now that we have our data, let's start the hypothesis testing. So what we'll want to do first is get the null and alternate hypothesis. So I'd say that the null hypothesis would be mu sub d for difference would equal 0, because we're trying to see, alright, is there any difference? We believe there's 0 now, we're going to see if there is any, or if it improves. And then we're going to say alternate hypothesis h sub a, mu sub d, is greater than 0. So we want to see if the difference, if it's greater than 0, that means there's less time for the scented time. That means there's been an improvement from scented. Now we must define our variables. So we have mu sub d equals the difference given time to solve a randomized puzzle, a paper and pencil maze, so my apologies, while wearing a mask, that is unscented, minus the time it takes to solve a pencil and paper maze while wearing a mask that is scented with a floral scent. This might take a long time, but at least you know what you're determining. It's also good to include, let's say, what you're doing. You could say, in parentheses, unscented minus scented. If you include this again, it's good to keep track of what you're doing. So now, you have to define your significance level. So you'd say alpha, it wasn't given to you, so it's say equals 0.05. And now it's time to do the checks. Never forget the checks, or else you get a couple points off on your quiz when it comes around. So your checks, start with normal. We would need to use, we can't use the NP is greater than 10 because we don't have a probability. So we have to check if N is greater or equal to 30. N here is 21. So since 21 is not greater than 30, we must look deeper. So on our calculator, if we open up stat and then edit our table, we're going to want to include in list 1 the difference in seconds that the table that we've made in L1. As soon as you do that, check back. I'm going to do it quickly, and I'll be back. So I finished putting in all my data in list 1. So what you want to do is go second y equals, go to stat plot, and then go to the first one. Make sure you turn it on, and then when you go to type, go to the far one all the way to the, you keep pressing the right. This is the normal distribution check. So you make sure that if it's linear, it's mainly normal. You press data list, L1, make sure it's X, and then choose whatever mark you'd like. Then if you press zoom, and then you scroll all the way down to zoom stat, it's going to zoom up right and easily for you. And as you can see, it's very normal. It's very straight. So since it's straight, we can assume it's normal. But you want to write down cumulative frequency, or normal distribution, linear regression, approximately linear. And then you can say, because of that, it's normal. So that's one check out of the way. The next one will be independent. This, you have to use your 10% rule. So you will use 1/10 of the total population has to be less than or equal to the sample population. You know the sample population is 21. So you just do a little algebra, and it has to be, the total population has to be greater than 210 students. Then just make sure that the grader sees this properly. You should write assume more than 210 students exist. Alright, so that'll cover your independent. So you could say that's independent check, left one more, random. This, it states how each subject works in the maze random order, but it doesn't say the subject will pick at random. But you have to assume it's random, assume it was an SRS picking them. So, just SRS, assume random, and then just say that's random. You're not going to want to say assume not random, or else you'll not be able to finish the problem. So you assume random, that's your 3 checks, move on to the rest of the problem. So, getting out some variables and numbers, you know that n, your population, is 21, as you can see. N is 21. If you go back to statistics and go to calculate 1var stats, L1 is list, frequent list is 0, calculate, it's going to give you a whole lot of data that you can use. Like it says n is 21, which we already know. We're going to want to record s sub x, which in this case equals 12.54. And we're also going to want to record x bar, which is 0.956. Always truncate, don't round. Alright, now that we've got this, we can tell we're going to have to start with our test statistic. But we don't know the population of our sample, of our, we do not know the standard deviation of the population, but we know the standard deviation of the sample, which we're given here. So, to do this, that means we're left with the t test statistic. So we'll have t equals x minus mu naught over s sub x over root n. I believe we're given everything here already. So we have x, which is 956, minus 0, which is given up here, over 12.54 over root 10, or root 21, because that's our n value. And then you just use some algebra. You go 0.956 minus 0, that's the numerator, 12.54 over 12.54 over the square root of 21. Then you divide one over the other. You get the statistic is 0.349. This is t. Now, to find your p-value, you could either look in table A or B in the back of the book, or you can use the TCDF function on your calculator. To do this on a test, you want to write out what you're using, what your parameters are when you're putting it down. So, when you do TCDF, you take your, if you have a greater than here, you will have your test statistic, 0.349, then a really large number. I usually go like 10,000. Then you go to your degrees of freedom. Degrees of freedom, by df, is equal to n minus 1. In this case, 21 minus 1 is 20. So that's our degrees of freedom. On our calculator, you can find that by going, if you go second 0, brings you to catalog. Then you press the 4 key, it's going to bring us the T's. Scroll down, you'll see TCDF. And type in exactly what you have here, 0.349, 10,000, 20. Make sure you have commas in between, press enter, gives us the number 0.365. This is our p-value of the null hypothesis. And now we want to compare this p-value to our alpha. So you know alpha is 0.05 and this is 0.365. And this is a big difference. The probability of H naught is way larger than alpha, so we must fail to reject. It's the null hypothesis. So now we have to have an explanation to determine why we're choosing this. So we can always start out with, since our p-value of, and include the p-value is 0.365, is much larger than the alpha value of 0.05, we can determine that the above data is not statistically significant. Because of this, we must fail to reject H null. The above data does not support the claim that wearing a pleasantly smelling helps solve a pencil and paper maze. So you need this extra last part so you include their context when you're talking about the problem here. However, the first two sentences are very cut out. So you always want to say, like, since our p-value, and compare that to our alpha value, we can determine that this is or is not statistically significant, depending on if you fail or fail not. You don't fail to reject or reject. Because of this, we must either fail to reject or reject, and then you go into your context. So at this point, this is the finish of the problem. You make sure that you use your math right, you do your checks, you use your TCDF, write out your parameters, and then compare and correctly get to the right conclusion. So we're going to try another problem. It's going to be a little bit more difficult, and see how we do. So we've got another problem here. It's about fertilizer success. I'll read it out. A farmer decides to try out a new fertilizer on a test plot containing 10 stalks of corn. Before applying the fertilizer, he measures the height of each stalk. 2 weeks later, he measures the stalks again, being careful to match each stalk's new height to its previous one. The stalks would have grown an average of 6 inches during that time, even without the fertilizer. Did the fertilizer help? Using a significance level of 0.05. So, as you can see, we have 2 samples here. We want to make into 1. This means we have to use a paired T procedure. So we're going to want to make another spot for difference height. You want to mark it all down of the change. So difference here would be 9.8 inches, 4.3 inches, 7.4, 8.4, 8.6, 5.5, 4.2, 9.7, 8.4, 7.3. Here, you will want to get the after height minus the before height to see the difference of time it changed. So include that here, after minus before. So make sure you know what you're solving. So now you have a new set of data, disregard all this up here, and you have all the rest of the stuff you need to do a normal a normal hypothesis test. So, first things first, let's get your hypothesis out here. Your null hypothesis. You will use mu sub d for the difference is equal to 6, because that's what it says here. An average is 6 inches. So you would say if it doesn't work, if nothing else happens, it's going to grow 6 inches. The alternate hypothesis would be that it grows greater than 6 inches. So you would say if the fertilizer works, then you say it grew more than 6 inches on average. Then define your terms. mu sub d is the difference of stalk height in inches from 2 weeks after the application of the fertilizer to when the fertilizer was applied. And you can put in quotes after, before. So basically you're determining here the difference of stalk height in inches between when it was placed and 2 weeks after when the fertilizer was placed. So now define your significance level. It's stated here, use significance level of 0.05. No difference of what we have been using anyway. Next, you do your checks. So test normal. You don't have a probability, so you're going to want to use n has to be greater or equal to 30. But we've got 10. 10 is not greater or equal to 30. Because of this, we should use our normal linear regression line on our calculator. To do that, don't want to do that during a stat test. I want to make sure that we have batteries. But go to stat, edit. Let's clear out this old data from the last problem and plug in the difference of height from here. So we have 9.8, 4.3, 7.4, 8.4, 8.6, 5.5, 4.2, 9.7, 8.4, and 7.3. That's 10 sets of data. Then, as we did before, go to stat plot. The plot still is probably on. Make sure it's on the linear regression line, X, and list 1. If you go to zoom 9, it's going to go zoom stat, and that's fairly linear as well. So we say normal linear regression is approximately linear. So you could say that's normal. One check out of the way. Independent. The 10% rule. 1/10 of n must be greater than or equal to the sample population. Sample population is 10, so n has to be greater than or equal to 100. So you have to write assume more than 100 stalks of corn, that's what we're using, exist. Of course there's over 100 stalks of corn, so it may seem redundant that we're writing that down, but we have to do it anyway. So because of that, independent, second check out of the way. Third check, random. Whenever you're given a problem with test plots in farming, you will always have random sampling. So you could also have to assume random. So you just write assume random SRS random sampling check done. So that's the checks. Let's start the problem. So writing out some information, n equals 10. If we go back to our calculator and go to stat, one variable stats, here we are, x bar equals 7.36, s sub x equals 2.05. We also have to use the t statistic here because we're given a sample, we're not given the entire population. So we're going to have x minus mu over s sub x over root n, as we did the last problem. Plug in some numbers. We're given that right here. So we have 7.36 minus 6 from here, over 2.05 over root 10. And this, if you plug it on right in our calculator, 7.36 minus 6, 2.05 over root 10, this divided by here, you're given with a t-score of 2.09. Also, and now you want to find our p-value. So, since this is greater than, you're going to want to keep TCDF start with this value, 2.09, large number, another 10,000, and then degrees of freedom. Degrees of freedom is n minus 1, 10 minus 1 equals 9, so we'll have 9 degrees of freedom. Same thing as last time, you go to catalog, 4 goes to T, TCDF, 2.09, comma, 10,000, comma, 9. Now we're given a value of 0.033 as our p-value. Now let's compare this p-value to our alpha. So, probability of null hypothesis and alpha. Alpha is 0.05 and this is 0.033. In this case, alpha is greater. Because of this, we must reject the null hypothesis. Now that we reject the null hypothesis, we have to do our explanation. So, let's see if we can write it out. Since our p-value of 0.033 is less than the alpha value of 0.05, we must reject H null and assume H sub A. The data above provides enough evidence to conclude that, and this is when you want to include your context, that the change of height, of stalk height, so you take change the stalk height, and you want to almost copy it from here, from 2 weeks after the application of the fertilizer to the time of the application of the fertilizer. Because we reject, we have to assume no hypothesis, and this says that the average height, or the average increase, is greater than 6. So we can say that the change is greater than 6 inches, which proves that fertilizer helped the growth of the corn plant. Here, we just gotta make sure we have everything. We have our hypotheses, we have defined our significance level, we have defined our variable. We have gone through our checks, normal, independent, random, got our variables with numbers, we are using a t-statistic, TCDF and our parameters, p-value, we have compared it to alpha, and we have described using the direct comparison and the context. So we have completed this problem again. We have proved that we must reject H null and that the fertilizer did help. So we want to say, yes, the fertilizer did help. That's all you really need to know about paired T procedures. It's not much harder, but I believe that if you go through on the AP and you see 2 samples, you have to find significance test, or not significance test, you have to find hypothesis testing. There you go. You can just know, alright, find the difference, make sure you read the problem, but you could see, alright, looks like you have to find the difference between these two and go through normal hypothesis testing. So, Ms. Cooper, I'm going to give you a little easier time. You could just say, I'm done grading. Here you go, Ms. Cooper. Thank you, and have a nice time. Good luck on the AP, whoever else is watching this.